Out there in the cold, distant reaches of our solar system, beyond the orbit of Neptune, a small world spins silently in the dark, a world so strange and mysterious, it's earned a name that sounds like something from an ancient myth. Makemake, this icy dwarf planet hidden in the Kuiper Belt, is one of the most enigmatic objects we've ever discovered, and yet, for most of human history, we had no idea it even existed. It wasn't until 2005 that astronomers finally spotted it, a faint speck of light moving against the backdrop of stars. But once we saw it, the questions began piling up. Why is its surface so bizarrely shiny? What's hiding beneath its frozen exterior? And why does it seem to defy so many of our expectations about how distant worlds should behave? Makemake is more than just another rocky body drifting in space. It's a puzzle wrapped in an enigma, a place where the rules we thought we understood about the outer solar system seem to break down. For years, scientists have been piecing together clues, trying to unravel its secrets, but every answer only leads to more questions. Some of these mysteries could rewrite what we know about how planets form, while others hint at forces and phenomena we've never seen before. And that's exactly what makes Makemake so thrilling. It's not just a dead, frozen rock. It's a dynamic, active world, one that might hold the key to unlocking some of the biggest cosmic puzzles out there. Today, we're going to dive deep into the 25 most baffling mysteries surrounding Makemake, from its strange, reflective surface that glows like a cosmic mirror to the mind-bending possibility that it could harbor hidden oceans beneath its icy shell. We'll explore why it lacks an atmosphere when other dwarf planets like Pluto have one, how its bizarre orbit might reveal the existence of unseen worlds lurking even farther out, and what its reddish color tells us about the violent history of the early solar system. This isn't just a tour of distant space rocks, it's a journey into the unknown, where every discovery challenges what we thought we knew. So buckle up, because by the time we're done, you'll never look at the outer solar system the same way again. The first mystery that grabs your attention when you study Makemake is its uncanny color. Unlike the pale grays and blues of most icy bodies in the Kuiper Belt, this dwarf planet glows with a distinct reddish-brown tint, like rust smeared across a cosmic snowball. At first glance, you might think it's just a trick of the light, but the more astronomers looked, the clearer it became. Makemake's surface is stained with something strange, something that shouldn't exist in such a cold, lifeless place. And that's where the real puzzle begins. The leading theory points to Tholen's complex organic molecules formed when sunlight breaks down simpler compounds like methane or nitrogen. Think of them as nature's graffiti artists splashing rusty hues across planetary surfaces. When ultraviolet radiation from the distant sun hits methane ice on Makemake, it triggers a chain reaction, creating these reddish-brown polymers. But here's the twist. Other Kuiper Belt objects have methane too, and they don't look like this. Pluto, for example, has patches of tholins, but its surface is a chaotic mosaic of whites, blues, and oranges. Makemake, on the other hand, wears its color like a uniform coat of paint. So why is it so different? One possibility is that Makemake's methane isn't sitting on the surface the way it does on Pluto. Instead, it might be locked beneath a layer of fresher ice, only exposed in rare, dramatic events like cosmic landslides or geysers erupting from below. Every time a chunk of terrain collapses or a plume of gas bursts forth, it could release a fresh dose of methane into the sunlight, kickstarting the chemical process all over again. Over millions of years, these tiny bursts of activity could have painted the entire world in this eerie shade. But there's another, even wilder idea. What if Makemake's color isn't just from tholins? Some scientists speculate that unknown compounds, molecules we haven't even discovered yet, might be lurking in its ice. The outer solar system is a chemical playground, far more diverse than we ever imagined. Every time we send a probe or point a telescope at these distant worlds, we find substances that defy our textbooks. Could Makemake be hiding one of those curveballs? Then there's the question of time. The reddish hue isn't static, it seems to shift slightly as Makemake rotates. That suggests the coloring isn't evenly distributed. Some regions might be newer, less stained by radiation, while others could be ancient battlegrounds where chemistry has been raging for eons. It's as if the planet's surface is a palimpsest, layers of history written in pigments we're only beginning to decode. And here's the kicker. If tholins are indeed the culprit, they're not just a pretty stain. These molecules are the building blocks of more complex organic material, the kind that, under the right conditions, could lead to life. Now, Makemake is far too cold for life as we know it, but the mere presence of these compounds raises tantalizing questions. Could similar processes on other worlds, warmer or more sheltered, have set the stage for biology? The redness of Makemake might be more than a curiosity. It could be a clue, a whisper from the cosmos about how chemistry becomes something greater. So when you look at that faint, reddish dot in telescope images, remember, you're not just seeing a frozen rock. You're seeing a laboratory, a canvas, a puzzle that's been baking under starlight for billions of years. And we've only just begun to read its story. If Makemake's rusty hue wasn't puzzling enough, its lack of an atmosphere deepens the mystery. This tiny world is roughly 2/3 the size of Pluto, large enough that scientists expected it to cling to at least a wispy shroud of gases. Yet when astronomers trained their instruments on Makemake, they found nothing. No haze, no detectable pressure, just the icy vacuum of space pressing against its barren surface. So why does this dwarf planet, so similar to Pluto in many ways, seem to have missed out on one of the most fundamental features of planetary bodies? The answer might lie in a cosmic game of hide and seek between heat, chemistry, and sheer dumb luck. Pluto's atmosphere, tenuous as it is, exists because of a delicate balance. The dwarf planet's surface ices, particularly nitrogen, methane, and carbon monoxide, sublimate under the faint warmth of the distant sun, creating a temporary gaseous envelope. But Makemake orbits even farther out, where sunlight is a mere whisper. At that distance, most substances would stay frozen solid, which begs the question, why doesn't Makemake at least have a whiff of methane gas given its reddish surface stains? The key might be in what's missing. Unlike Pluto, Makemake's surface appears dominated by methane alone, without the nitrogen or carbon monoxide that helps sustain Pluto's atmosphere. Nitrogen acts like a buffer, slowing down the escape of other gases into space. Without it, any methane vaporizing from Makemake's surface could be vanishing almost as fast as it forms, like a pot of water boiling dry the moment it hits the stove. But there's another twist. Makemake's orbit isn't just distant, it's weirdly circular compared to Pluto's elongated path. That means it never gets close enough to the sun for even a seasonal thaw. Pluto's elliptical orbit brings it periodically nearer to the sun, triggering temporary atmospheric surges. Makemake, stuck in its frosty rut, might have lost whatever atmosphere it had billions of years ago, leaving it permanently exposed. Then again, perhaps the absence of an atmosphere isn't permanent at all. Some researchers speculate that Makemake could be a seasonal world, with gases trapped beneath its ice like a shaken soda can waiting to erupt. On Earth, we see this in places like Saturn's moon Enceladus, where geysers blast material into space. If Makemake has underground reservoirs of volatile ices, or even hidden geothermal activity, it might sporadically puff out a fleeting atmosphere before it all freezes or escapes. The most tantalizing clue comes from a fleeting observation in 2011, when Makemake passed in front of a distant star. Astronomers expected the star's light to wink out abruptly as the dwarf planet's solid edge crossed it. Instead, there was a faint, gradual dimming, a hint that something might be clinging to Makemake after all. Perhaps a transient haze or localized gas venting from its surface. If true, it would mean this world isn't entirely lifeless, it's just playing by rules we don't yet understand. What makes this absence so fascinating isn't just the science, it's what it tells us about the diversity of the solar system. Two dwarf planets similar in size and origin, yet one wears a tattered cloak of gases while the other stands bare. That disparity forces us to rethink how atmospheres form, persist, or vanish in the outer darkness. Maybe Makemake is a cautionary tale, a reminder that even in the coldest reaches of space, the line between a living world and a frozen relic can be razor thin. Or maybe it's hiding secrets beneath its ice, waiting for the right moment to exhale. One of the most baffling things about Makemake isn't just what's there, it's what isn't. While nearly every other dwarf planet in the Kuiper Belt dances with at least one moon, Makemake spins in solitary silence. Pluto has Charon, Hydra, and Nix. Haumea boasts two fast-orbiting companions. Even Eris, Makemake's distant cousin, has a moon named Dysnomia, but Makemake nothing. Not a single satellite has been detected, and that absence isn't just odd, it's a direct challenge to everything we thought we knew about how these icy worlds form. For decades, astronomers assumed moon formation was practically inevitable for objects this size. The prevailing theory goes like this: when large Kuiper Belt objects collide, the debris from the impact doesn't just vanish, it coalesces into moons. Pluto's largest moon, Charon, likely formed this way, a cosmic splinter from a violent crash billions of years ago. Haumea's moons, probably shards from a long-ago collision that left the dwarf planet spinning wildly, stretched into an egg-like shape. But Makemake's pristine, uncracked surface and empty orbital neighborhood suggest a different story. Did it somehow avoid these chaotic encounters, or is something else at play? One possibility is that Makemake did have moons once, they just didn't stick around. In the chaotic early solar system, gravitational tugs from nearby giants like Neptune could have stripped them away, flinging them into the void or sending them spiraling back into Makemake's surface. Without a stabilizing companion to keep its rotation in check, Makemake might have even absorbed its own moons over time, swallowing them like a cosmic game of planetary Pac-Man. Then there's the question of detection. Moons in the Kuiper Belt are notoriously hard to spot, tiny, dark, and often lost in the glare of their parent bodies. Some of Pluto's smaller moons weren't discovered until the New Horizons mission flew by in 2015. Could Makemake have a hidden moon too small or too faint for our current telescopes to see? There's precedent. When astronomers first studied Eris, they thought it was moonless until deeper observations revealed Dysnomia lurking in its shadow. But even if a moon is hiding, its absence from current data tells us something profound. Makemake's environment might be uniquely stable, untouched by the gravitational chaos that shaped its neighbors. Or perhaps its formation was gentler, without the violent collisions that littered other dwarf planets with orbiting debris. Either way, this solitary existence forces us to reconsider how diverse planetary systems can be. Not every world follows the same blueprint, and that's what makes Makemake so intriguing. It's not just a missing moon mystery, it's a reminder that the universe always keeps a few surprises up its sleeve. Makemake's orbit isn't just a simple loop around the sun. It's part of an intricate gravitational ballet, one that ties it to Neptune in a way that defies simple explanations. This dance, known as an orbital resonance, means that for every 11 times Neptune circles the sun, Makemake completes roughly 6 orbits. It's not a perfect ratio, but it's close enough to suggest something profound. Neptune's gravity has been tugging at Makemake for billions of years, shaping its path in ways we're only beginning to understand. And that raises a tantalizing question. Was this resonance always there, or is it a clue to a far more chaotic past? Resonances like this aren't unheard of in the solar system. Pluto, for example, is locked in a 2-to-3 resonance with Neptune, ensuring the two never collide despite their crossing orbits. But Makemake's 11-to-6 rhythm is far less common, and that rarity hints at a turbulent history. Some scientists believe this resonance could be a cosmic fossil, a remnant from the solar system's infancy when planets and dwarf planets were still jostling for position. Back then, Neptune's migration outward, a phenomenon known as the Nice Model, would have sent shockwaves through the Kuiper Belt, scattering icy worlds like billiard balls. Makemake might have been one of the survivors, captured into this strange rhythm as Neptune's gravity herded it into place. But there's another, even more intriguing possibility. What if Makemake's resonance isn't just about Neptune? Some researchers speculate that an unseen, far more distant planet, often called Planet 9, could be pulling strings from the shadows. This hypothetical world, thought to lurk in the outer solar system, might subtly alter the orbits of objects like Makemake, tweaking their paths in ways that don't quite fit our current models. If true, Makemake's odd resonance could be a breadcrumb trail leading us to one of astronomy's biggest unsolved mysteries. The resonance also raises questions about stability. Unlike Pluto, whose orbit is locked into place by its resonance, Makemake's dance with Neptune is messier, less precise. That slight imperfection suggests its orbit might not be set in stone. It could evolve over time, drifting in or out of resonance as gravitational forces shift. Some simulations even show Makemake slipping free entirely, untethered from Neptune's influence after millions of years. So why hasn't that happened yet? Is some unseen force keeping it in line, or are we catching it at just the right moment in a slow, cosmic unraveling? Then there's the puzzle of Makemake's neighbors. Other large Kuiper Belt objects like Haumea don't share this resonance, so why does Makemake? The answer might lie in its size. As one of the largest known objects in the region, Makemake would have been a prime target for Neptune's gravitational nudges, more likely to be corralled into a stable orbit than smaller, less massive bodies. But that still doesn't explain why it ended up in this specific rhythm while others didn't. What makes this resonance so fascinating isn't just the mechanics, it's what it reveals about the solar system's hidden dynamics. Makemake's path is a record of forces we can't see, a fingerprint of events that happened billions of years ago. Every slight wobble, every deviation from expectation, might be a clue to something greater. A lost chapter in our cosmic history, or perhaps a signpost pointing toward discoveries we haven't even imagined yet. So when you look at Makemake's orbit, remember, you're not just seeing a frozen world circling the sun. You're seeing a story written in gravity itself, one we're only just learning to read. Makemake doesn't just sit quietly in the darkness it flickers. Astronomers have long noticed something bizarre about this distant world. Its brightness isn't steady. Instead, it pulses unpredictably, dimming and brightening in ways that defy easy explanation. At first, scientists assumed these variations were just surface quirks, maybe patches of darker and lighter terrain rotating in and out of view. But the more they studied it, the stranger the puzzle became. These fluctuations aren't just slight dips in luminosity. Some are dramatic enough to suggest something far more dynamic is at play beneath that icy crust. Could hidden geologic forces be reshaping Makemake's surface in real time? The leading suspect is cryovolcanism, the eruption of volatile substances like water, methane, or ammonia instead of molten rock. On other icy worlds like Saturn's moon Enceladus or Neptune's Triton, cryovolcanoes blast plumes of material into space, creating ever-changing landscapes. If Makemake harbors similar activity, even sporadically, it could explain the brightness shifts. Imagine a geyser of slushy ice erupting from beneath the surface, spreading fresh, reflective material across the terrain. Over time, that new ice would darken under the bombardment of cosmic radiation, only to be covered again by another eruption. This cycle could create a patchwork of bright and dark regions, visible from Earth as subtle flickers in Makemake's glow. But there's a problem. Cryovolcanism usually requires an internal heat source, something to melt the ice and fuel the eruptions. Makemake is far too small to retain much primordial heat, and with no large moon tugging at its core, tidal heating seems unlikely. So where's the energy coming from? One theory points to radioactive decay in its rocky interior, slowly releasing enough warmth to keep pockets of subsurface sludge in motion. Another possibility is that Makemake's orbit isn't as stable as we think. Subtle gravitational nudges from Neptune or other unseen forces could be flexing its interior, generating just enough friction to spark occasional outbursts. Then there's the wild card, seasonal changes. Unlike Earth, where seasons are driven by axial tilt, Makemake's brightness shifts might stem from its extreme distance from the Sun. Even tiny variations in solar radiation, like those caused by the Sun's natural activity cycles, could trigger sublimation or refreezing of surface ices. Picture a layer of methane frost vaporizing under a slight uptick in sunlight, leaving behind darker, tholin-stained ground. Later, as temperatures drop again, fresh frost might recondense, restoring the bright sheen. These micro-seasons could unfold over decades, creating the irregular patterns we observe. But the weirdest possibility, Makemake might be spinning oddly. Most spherical objects rotate smoothly, but some, like Haumea, tumble chaotically due to past collisions. If Makemake's rotation is unstable, wobbling like a poorly thrown football, it could expose different surface features to Earth's line of sight at unpredictable intervals. That would make its brightness variations less about geology and more about simple geometry. The trouble is, we haven't detected any dramatic shape irregularities to support this idea. So unless Makemake is hiding a subtle deformity, the mystery deepens. What makes these brightness changes so compelling isn't just the scientific challenge, it's what they imply about Makemake's nature. A static world wouldn't flicker like this. Something is stirring beneath that frozen facade, whether it's the slow churn of radioactive decay, the occasional belch of a cryovolcano, or the whisper-thin dance of frost and sunlight. Every flicker is a clue, a glimpse into the hidden life of a world we're only beginning to understand. And that's the beauty of Makemake. Even in the darkest reaches of the solar system, nothing stays still forever. Makemake's surface holds a glaring contradiction. It should be drowning in methane, yet somehow it's not. Given its reddish hue and frigid environment, scientists expected vast plains of methane ice, similar to Pluto's heart-shaped Tombaugh Regio or the cracked plains of Neptune's moon Triton. Instead, observations reveal only trace amounts, as if the methane vanished into thin air, or more accurately, thin space. This absence isn't just curious, it flips our understanding of icy worlds upside down. If methane isn't blanketing Makemake, what's covering its surface, and where did all that expected carbon go? The mystery deepens when you consider how methane behaves in the Kuiper Belt. On Pluto, it's everywhere, mixed with nitrogen, frozen into glaciers, even floating in the atmosphere. On Eris, another methane-rich dwarf planet, the compound lingers in thick, sluggish layers. But Makemake, sitting squarely between them in size and temperature, seems to have rejected the trend. One theory suggests its methane isn't missing at all, it's just hiding. Unlike Pluto, where methane mingles with softer ices like nitrogen, Makemake's surface might be dominated by harder, more rigid methane hydrates. These cage-like structures trap methane molecules inside water ice, making them harder to detect with telescopes. Imagine a cosmic magician's trick. The methane is still there, just locked away in icy vaults. Then there's the escape artist hypothesis. Methane, when exposed to sunlight, doesn't just sit still, it breaks apart. Ultraviolet radiation can strip hydrogen atoms from methane molecules, leaving behind reactive fragments that polymerize into those reddish tholins staining Makemake's surface. Over billions of years, this process could have devoured much of the original methane, leaving behind only a chemical graveyard. But here's the catch. This destruction should have left a clear spectral fingerprint, and the numbers don't quite add up. The tholins we see can't account for all the methane that should have been there. So where's the rest? A more radical idea involves chemistry we've never seen before. On Earth, microbes in oxygen-poor environments produce methane as a byproduct. Of course, Makemake is far too cold for life, but what if some abiotic process, unique to its extreme environment, is converting methane into something else entirely? Laboratory experiments show that under intense cold and radiation, methane can morph into complex hydrocarbons like ethane or even longer chains. These substances would look very different in telescope data, potentially explaining why our observations don't match expectations. The most tantalizing clue comes from Makemake's temperature. At nearly -240 degrees Celsius, its surface is colder than Pluto's, sitting right on the edge where methane's behavior gets weird. Under these conditions, methane ice doesn't just sublimate, it can undergo phase transitions, rearranging its molecular structure into exotic forms. Some of these phases might be invisible to our current instruments, or so volatile they vanish almost immediately after forming. If true, Makemake could be a laboratory for chemistry that exists nowhere else in the solar system. What makes this missing methane so fascinating isn't just the scientific detective work, it's what it says about how little we truly know. The outer solar system isn't just a colder version of the inner planets. It's a realm where familiar substances behave in alien ways. Makemake's methane mystery forces us to question assumptions, to consider that even the most basic building blocks of planetary science might have surprises waiting in the dark. And that's the real wonder here. Every time we think we've figured out the rules, a world like Makemake reminds us the cosmos always has another trick up its sleeve. Among the most perplexing features on Makemake are the dark patches scattered across its otherwise shiny surface, irregular smudges that stand out like ink blots on a mirror. These regions absorb sunlight rather than reflecting it, creating stark contrasts against the bright methane ice. At first glance, they might seem like simple impact scars, but the more astronomers study them, the less sense they make. Their distribution isn't random, their shapes aren't circular like typical craters, and their chemical signatures don't match what you'd expect from a collision. So what's really going on in these shadowy zones? The leading theory suggests these patches could be vast reservoirs of complex organic material, tholins, that have accumulated over eons. On other worlds, like Saturn's moon Titan, tholins form naturally when sunlight breaks down methane and nitrogen, creating a sticky, tar-like substance. But Makemake's dark areas don't behave like Titan's dunes. They're more localized, almost as if they're seeping up from below. One provocative idea is that these patches might be the remnants of ancient cryovolcanic activity, where slushy mixtures of water, ammonia, and organics erupted onto the surface and then darkened under relentless cosmic radiation. Picture a frozen volcano spewing not lava, but a slurry of primordial ooze that slowly baked into a charcoal-like crust over billions of years. Another possibility is that these dark zones are the scars of something far more dramatic, cataclysmic impacts that punched through Makemake's icy shell and exposed a deeper, darker layer beneath. On Jupiter's moon Europa, for example, strikes from comets or asteroids sometimes reveal briny, discolored subsurface material. If Makemake has a similarly layered interior, impacts could have dredged up darker compounds from its depths. Yet the patches don't show the raised rims or ejector patterns typical of impact sites. Instead, they look almost smeared, as if something had dragged them across the surface. Then there's the wild card. Could these dark regions be evidence of seasonal changes? On Pluto, the heart-shaped Sputnik Planitia shifts slightly in composition and reflectivity as ices sublimate and recondense over decades. Makemake's dark patches might be the result of similar processes, pockets of volatile ices that vanish when warmed by the faint sun, leaving behind concentrated residues of darker material. Over time, these residues could clump together, forming the blotches we see today. But the most tantalizing question isn't just what these patches are, it's why they're so unevenly distributed. Some appear clustered near Makemake's equator, while others are suspiciously absent from certain longitudes. This asymmetry hints at something fundamental about the dwarf planet's geology or climate. Maybe its rotation or internal heat distribution favors dark material gathering in specific zones, or perhaps ancient tectonic fractures channeled organic rich slush to the surface in select areas. What makes these dark patches so compelling is the sheer number of possibilities they represent. They could be scars from impacts, stains from cryovolcanic leaks, or even the fingerprints of a long-lost subsurface ocean. Every explanation opens new questions, and every unanswered question reminds us how much we still don't know about the frozen frontiers of our solar system. For now, these Inkai smudges remain one of Makemake's most stubborn secrets, a puzzle written in shadows, waiting for the right light to reveal its meaning. If there's one thing you'd expect from a world as distant as Makemake, it's consistency, a frozen, unchanging wasteland where temperatures hover near absolute zero. But the universe loves a good curveball. Observations reveal that Makemake's surface doesn't just stay uniformly cold. It fluctuates in ways that defy even the most careful calculations. Some regions are slightly warmer than they should be, others cooler, and these variations aren't random. They follow patterns that suggest something beneath the ice is stirring, quietly reshaping our understanding of what's possible in the outer solar system. At first glance, Makemake's temperature should be a simple equation. Sunlight at that distance is feeble, providing barely enough energy to keep a thermometer reading at around -240 degrees Celsius. Yet infrared scans show pockets where the numbers don't add up. Certain areas, particularly near the darker patches, absorb more heat than their surroundings, while shiny, reflective zones stay colder. This isn't just a surface phenomenon. It hints at differences in composition or even hidden geothermal activity. On Earth, we'd attribute this to volcanism or weather, but Makemake isn't supposed to have either. So what's really going on? One possibility is subsurface chemistry. Methane, the same compound staining Makemake's surface red, has an unusual property when trapped in ice. It can trap heat like a thermal blanket. If methane hydrates exist beneath the crust, they could create insulating layers, slowing the escape of whatever meager warmth trickles up from the dwarf planet's core. Picture a buried network of icy sponges, each pocket holding onto traces of heat and releasing it unevenly to the surface above. Then there's the wild card of radiative cooling. Makemake's surface ices, especially methane, don't just reflect or absorb sunlight, they also emit energy back into space, but different ices do this at different rates. Fresh, clean methane ice might cool efficiently, while tholin-stained patches retain heat longer, creating localized temperature spikes. It's like comparing a polished mirror to a charcoal briquette. One bounces light away, the other soaks it up. But the most tantalizing explanation involves internal heat. Makemake is too small to retain much primordial warmth, but it might not need much. Radioactive decay in its rocky core could produce just enough energy to create subtle temperature gradients. Even a whisper of geothermal activity could explain why some areas seem anomalously warm. We've seen this on Pluto, where an insulated subsurface ocean might still be liquid billions of years after formation. Could Makemake, against all odds, harbor similar secrets? The implications are profound. If Makemake's temperature variations stem from internal processes, it challenges the long-held assumption that small, distant worlds are geologically dead. Instead, they might be ticking quietly, their engines running on slow, cosmic timescales. Every flicker of warmth, every unexpected hotspot could be a clue, not just about Makemake, but about the hidden lives of all the frozen worlds at the edge of our solar system. And that's the real mystery here. The more we learn, the less we realize we truly know. Measuring time on Makemake sounds simple. Just clock how long it takes to rotate once, but this dwarf planet laughs at simplicity. Scientists have spent years trying to pin down its exact rotation period. and the results keep slipping through their fingers like ice under sunlight. Some studies suggest a little under 8 hours, others point to 22. That's not a minor discrepancy, it's the difference between a dizzying spin and a leisurely day. So why can't we nail down something as fundamental as how fast Makemake turns? The answer lies in a perfect storm of cosmic obstacles, from its devilishly reflective surface to the eerie quiet of its orbit. First, there's the problem of light. Makemake's mirror-like surface reflects so much sunlight that subtle brightness variations, the kind used to calculate rotation, get drowned in glare. Imagine trying to read a flickering candle in front of a spotlight. Even Hubble, our sharpest eye in the sky, struggles to detect the faint patterns that would betray its spin. Compounding the issue, Makemake's surface isn't uniformly reflective. Those mysterious dark patches absorb light differently than the bright methane ice, creating a kaleidoscope effect that distorts measurements. One hemisphere might dominate the signal for a while, then vanish as the other rotates into view, tricking instruments into seeing phantom rhythms. Then there's Makemake's solitude. Most rotating objects have a moon or two acting as cosmic metronomes. Their orbits reveal the parent body's spin through gravitational interactions. Pluto's rotation, for example, is precisely known thanks to Charon's rhythmic dance. But Makemake, alone in the void, offers no such clock. Without external markers, astronomers are left guessing based on flickers of reflected light, a method prone to error when dealing with a world this shiny and distant. The plot thickens when you consider axial tilt. Earth's poles point roughly the same way year-round, but Makemake might be wobbling chaotically, its axis shifting unpredictably over time. This phenomenon, called longitudinal libration, could stretch or compress the apparent rotation period depending on when and how we observe it. Picture a spinning top that occasionally veers off-center. From our vantage point, Makemake's day length could appear to fluctuate even if its true rotation stays constant. Perhaps the most intriguing possibility, Makemake isn't spinning uniformly at all. Some icy worlds, like Saturn's moon Hyperion, tumble erratically due to irregular shapes or past collisions. If Makemake's rotation is genuinely variable, accelerating or slowing under subtle forces, that would explain why no two studies agree. It might also hint at hidden internal dynamics, like a subsurface ocean sloshing beneath the ice, altering the dwarf planet's moment of inertia over time. Every failed attempt to lock down Makemake's rotation teaches us something new. The very elusiveness of this measurement reveals how strange and dynamic this world truly is. What seems like a simple question, how long is a day, turns out to be a portal into deeper mysteries of light, shadow, and the silent forces shaping worlds at the edge of the solar system. Until we send a probe to watch Makemake spin up close, its rotation remains a riddle wrapped in ice, daring us to look closer. From a distance, Makemake appears as a perfect icy sphere, but zoom in closer and the picture gets far more interesting. Most dwarf planets bulge slightly at their equators due to rotational forces, but Makemake's shape teeters on the edge of detection, leaving astronomers debating whether it's truly round or hiding subtle deformities. The clues we have paint a fascinating portrait, a world that might be stretched, dented, or even bearing the scars of ancient cataclysms beneath its polished exterior. The first hints came from stellar occultations, those rare moments when Makemake passes in front of a distant star, casting a shadow that reveals its silhouette. During these events, astronomers expected to see a clean, symmetrical dip in starlight as the dwarf planet's edge blocked the star. Instead, the data showed tiny irregularities, almost like the star's light flickered as it grazed Makemake's limb. Some researchers argue these anomalies suggest a slight elongation, with the world's equator measuring just a few dozen kilometers wider than its poles. Others counter that surface features like towering ice mountains or deep basins could produce the same effect without implying a fundamentally oval shape. But if Makemake is stretched, that opens a cosmic can of worms. Rotational forces typically squash spinning objects, but Makemake's leisurely day, however long it may be, shouldn't generate enough centrifugal force to deform it noticeably. Unless, of course, its rotation was once much faster. Many icy worlds in the Kuiper Belt bear the marks of violent collisions, cataclysms that could have sent them spinning wildly before gradually slowing down. Haumea, for example, spins so rapidly it's shaped like a squashed football. Makemake might be a quieter cousin, its elongation a whisper of past chaos rather than a shout. Then there's the question of density. A perfectly spherical shape suggests a relaxed, fluid interior that settled into hydrostatic equilibrium. A fancy way of saying gravity smoothed it into the most efficient form. But if Makemake's shape is irregular, it implies something rigid inside resisted that smoothing. Imagine trying to mold a snowball around a hidden rock. The tougher core would warp the exterior. On Makemake, that rock might be a dense silicate mantle, or even pockets of compressed methane clathrates acting like cosmic rebar beneath the ice, the most tantalizing possibility. Makemake could be hiding an ancient, fossilized bulge, a relic from when it had a moon. Many elongated worlds owe their shape to tidal interactions with orbiting companions. Without a moon today, Makemake's slight stretch might be the ghost of a gravitational dance long since ended, a partner lost to time. What makes this shape debate so captivating isn't just the geometry, it's what it tells us about how little we truly know. Even something as fundamental as a planet's form becomes a riddle when viewed across billions of kilometers. Every slight irregularity, every disputed measurement, hints at forces and histories we're only beginning to decipher. And that's the beauty of Makemake. It refuses to fit neatly into our models, reminding us that the universe always keeps a few secrets in reserve. Among the most tantalizing possibilities hiding beneath Makemake's icy shell is the potential for cryovolcanos, frosty equivalents of Earth's fiery mountains, where slushy mixtures of water, ammonia, or methane erupt instead of molten rock. While no plumes or lava flows have been spotted yet, the absence of evidence isn't evidence of absence. This distant world has already defied expectations at every turn, so why should geology be any different? The clues are subtle but persuasive. That strangely reflective surface, the fluctuating brightness, even the mysterious dark patches, all could hint at a restless interior occasionally forcing its way to the surface. Take cryovolcanism on other icy worlds as a blueprint. Saturn's moon Enceladus sprays towering geysers of water vapor into space, while Neptune's Triton boasts nitrogen-spewing vents that dust its surface with fresh frost. Both are smaller than Makemake, proving that size isn't the sole factor in sustaining such activity. What these worlds share, though, is a heat source, whether from tidal friction, radioactive decay, or residual formation energy, to keep their subsurface layers mobile. Makemake lacks the gravitational tug of a nearby giant planet to generate tidal heating, but it might not need it. Even a whisper of warmth from decaying isotopes in its rocky core could maintain pockets of liquid or semi-fluid sludge, trapped under pressure for eons until something gives way. Then there's the matter of methane. Its uneven distribution across Makemake's surface reads like a cosmic detective story. If the methane isn't uniformly coating the terrain, where is it coming from? One compelling answer: cryovolcanic outgassing. Periodic eruptions could release trapped methane from beneath the ice, where it then gets painted into tholins by sunlight. Unlike Pluto, where methane is mixed with nitrogen and carbon monoxide to form a stable atmosphere, Makemake's lone methane emissions might vanish almost instantly, explaining why we've never detected them. The dark patches could even be ancient cryovolcanic deposits, their organic rich residues baked dark by radiation over millennia. The real smoking gun, though, might lie in Makemake's shape. Some elongated or slightly distorted worlds owe their forms to internal dynamics, like a tube of toothpaste squeezed from within. If cryovolcanism has reshaped Makemake's surface over time, it could have left subtle bulges or depressions detectable by future missions. Even more telling would be the discovery of fresh, uncratered terrain, a sign that eruptions have recently resurfaced parts of the dwarf planet, erasing the scars of ancient impact. Of course, speculation isn't proof. What we need is a close-up look, and that's where future missions come in. Imagine a spacecraft like New Horizons, but designed specifically for the Kuiper Belt, skimming past Makemake with infrared scanners and high-resolution cameras. It could hunt for thermal anomalies, trace gas plumes, or even snap images of cryovolcanic domes. Even more revealing would be a lander, though that's a far greater technical challenge. Drilling through Makemake's ice to sample subsurface chemistry would settle the debate once and for all, revealing whether this distant world is truly dead or merely biding its time between eruptions. Until then, the possibility lingers like a shadow at the edge of our understanding. Cryovolcanos on Makemake would rewrite the rules for small, distant worlds, proving that geologic vitality isn't confined to the inner solar system. Every unexplained flicker of brightness, every odd temperature variation, becomes a clue waiting to be pieced together. And that's the thrill of exploration. Sometimes the most exciting discoveries aren't the ones we've made, but the ones still lurking just out of sight. The Kuiper Belt is supposed to be messy, a chaotic junkyard of ice, rock, and dust left over from the solar system's formation. Yet around Makemake, something's missing. Scans reveal a startling absence of fine debris in its immediate vicinity, as if someone swept the cosmic doorstep clean. This isn't just odd, it's downright suspicious. Other dwarf planets like Pluto and Haumea are surrounded by dusty halos, kicked up by micrometeorite impacts or the gentle outgassing of surface ices. But Makemake's neighborhood is eerily pristine, and that cleanliness might be the biggest clue yet to hidden forces at work. One explanation points to Makemake's bizarrely reflective surface. Most Kuiper Belt objects are dull, their ices darkened by eons of radiation. But Makemake's mirror-like sheen suggests its outer layer is constantly renewed, either by fresh frost condensing from a wispy atmosphere or by cryovolcanic resurfacing. If true, any dust settling on Makemake could get buried under fresh ice almost immediately, like snow covering footprints on a winter morning. Over time, this process would leave the dwarf planet's surroundings conspicuously bare. But there's a catch. Renewal alone shouldn't erase dust entirely. Even on Enceladus, where geysers constantly repave the surface, some particles escape to form Saturn's E-ring. Makemake's dust-free zone implies something more aggressive is at play. Perhaps its weak gravity, just 1/18 of Earth's, can't hold onto loose particles, allowing even gentle solar winds to blow them away. Or maybe its methane-rich surface chemistry acts like a cosmic glue, trapping dust grains the moment they land. Laboratory experiments show that methane ice under extreme cold can become sticky, clumping with other materials in ways water ice doesn't. The most tantalizing theory involves hidden electrical forces. On airless worlds like Earth's moon, sunlight can electrically charge surface dust, causing it to levitate. If Makemake's ultra-reflective ice amplifies this effect, dust might hover above the surface just long enough to be swept away by solar radiation pressure. This would create an invisible barrier, a kind of electrostatic moat keeping the dwarf planet's vicinity unnaturally spotless. Then there's the wild card, recent activity. A major impact or cryovolcanic eruption could have temporarily cleared the area, blasting dust outward faster than it could drift back. We've seen this on Mars, where global dust storms redistribute particles across the planet. If Makemake experienced a similar event within the past few thousand years, a blink in cosmic time, the evidence might still linger in its unexpectedly clean orbit. What makes this dust deficit so compelling isn't just the mystery, it's the implications. A dynamic surface, hidden forces, or even cataclysmic events could explain the void around Makemake. Every absent speck of dust whispers a question. Is this world far more active than we ever imagined, or does it play by rules we haven't discovered yet? One thing's certain, in the bustling debris field of the Kuiper Belt, Makemake's cleanliness isn't just unusual, it's a red flag waving in the cosmic wind. Makemake's solitude might not be as complete as it seems. While telescopes haven't spotted any moons orbiting this distant world, there's another hidden structure that could be lurking just out of view, a delicate ring system, faint as a whisper, clinging to the dwarf planet's gravitational embrace. This isn't just wild speculation, we've already seen it happen elsewhere. Haumea, another Kuiper Belt dwarf planet, sports two narrow rings despite its small size and rapid spin. So why not Makemake? The answer lies in a cosmic game of hide and seek where the rules keep changing. Rings around small bodies shouldn't be stable. Conventional wisdom says they'd either collapse into moons or dissipate into space within a few million years, a blink in geological time. Yet Haumea's rings defy that logic, surviving against all odds. Their existence suggests that rings might be far more common in the outer solar system than we ever imagined. If Haumea can have them, why wouldn't Makemake? The ingredients are all there, a mix of ice and rock debris left over from ancient collisions or tidal disruptions, suspended in orbit by Makemake's gravity. The real question isn't whether rings could form, it's why we haven't found them yet. The challenge is detection. Rings made of dark, fine particles like those around Haumea are nearly invisible to Earth-based telescopes. They don't reflect much light, and their thin profiles mean they're easily lost in the glare of their parent body. Makemake's dazzling brightness only compounds the problem. Its mirror-like surface could be drowning out the faint signature of any rings. Even if they're there, our current instruments might simply be blind to them. Then there's the orbit factor. Haumea's rings sit snugly within its Roche limit, the point where tidal forces would tear a moon apart. For Makemake, that zone is even smaller due to its weaker gravity. Any rings would need to hug the dwarf planet tightly, making them harder to distinguish from its surface in telescopic images. Worse still, stellar occultations, our best tool for spotting rings, haven't yielded clear hints. When Makemake crosses in front of stars, the light dips smoothly without the telltale flickers that betrayed Haumea's rings. But that doesn't necessarily mean they're absent. If Makemake's rings are patchy or misaligned with our line of sight, they could be slipping through our observational nets. The most intriguing possibility, Makemake's rings might come and go. Some models suggest that irregularly shaped bodies can generate temporary rings when their odd rotations fling surface material into orbit. These ephemeral halos could last for centuries before dissipating or clumping into moons. If we happened to study Makemake during a ringless phase, we'd never know the difference. What makes this debate so compelling isn't just the science, it's what it says about our place in the cosmos. Every time we assume something can't exist, the universe finds a way to surprise us. Rings around dwarf planets were once unthinkable. Now they're a tantalizing possibility. Whether Makemake hides its own celestial jewelry or stands truly alone, the search itself reminds us how much we have left to learn. And sometimes the most thrilling discoveries aren't the ones we make, but the ones still waiting, just beyond the edge of our vision. Makemake's name carries a weight far beyond its celestial identity. It's a direct bridge between the icy reaches of the Kuiper Belt and the sun-drenched legends of Earth's most isolated culture. The dwarf planet wasn't just randomly christened. Its title comes straight from the mythology of the Rapa Nui people, the indigenous inhabitants of Easter Island. In their traditions, Makemake wasn't merely a god, he was the creator of humanity, the bringer of fertility, and the master of the seabirds that sustained life on their remote island. So how did a Polynesian deity end up lending his name to a frozen world 4 billion miles away? The story begins with the International Astronomical Union's rules for naming dwarf planets. Objects like Makemake orbiting beyond Neptune in the Kuiper Belt must bear names rooted in creation myths. The choice was deliberate, just as the Rapa Nui Makemake watched over an island so isolated it felt like another world. His celestial counterpart reigns over one of the most distant known bodies in our solar system. There's poetry in the parallel. Both exist in extreme environments, both are shrouded in mystery, and both represent resilience against the odds. Easter Island's Makemake was often depicted with wide, staring eyes, a symbol of vigilance, while the dwarf planet's reflective surface seems to gaze back at us with an uncanny brightness, as if keeping watch over the cosmic ocean it drifts through. But the connection runs deeper than symbolism. The Rapa Nui people believed Makemake controlled the annual migration of seabirds, which brought vital resources to their island. In a way, the dwarf planet mirrors this role. It's a gravitational anchor in its own lonely stretch of space, potentially shepherding smaller objects in its orbital path. Even the timing of its discovery feels mythic. Astronomers spotted it just days after Easter in 2005, as if the universe itself nodded to the cultural tie. What makes this naming so resonant isn't just the homage, it's how perfectly it captures the dwarf planet's enigma. The Rapa Nui Makemake was both benevolent and inscrutable, a deity who gifted life but demanded reverence. His celestial namesake, too, balances revelation with secrecy. Every time we think we've understood it, whether it's surface chemistry, its lack of moons, or its temperature quirks, it reveals another layer of mystery. The name isn't just a label, it's an invitation to remember that even in the age of space telescopes, some things still hold the awe of the ancient world. And perhaps that's the most fitting tribute of all, a reminder that exploration, whether of Polynesian waves or planetary orbits, begins with wonder. If there's one chemical signature astronomers expected to find on Makemake, it's carbon monoxide. This icy compound is practically a staple in the outer solar system. Pluto's surface is peppered with it, Eris has traces, and even distant comets carry it like cosmic luggage. Yet when scientists trained their instruments on Makemake, they came up empty. The absence is so glaring it's like finding a snowman without a carrot knows something fundamental is missing, and the implications ripple far beyond a simple chemical inventory. Carbon monoxide isn't just another molecule, it's a thermometer for planetary processes. On Pluto, it mixes with nitrogen and methane to form glaciers that creep like slow-motion rivers. On Triton, it helps create geysers that erupt with icy fury. Its presence usually signals an active, dynamic world where chemistry never sleeps. So why would Makemake, so similar in size and composition to these other icy bodies, lack it entirely? The answer might lie in a cosmic disappearing act, one where sunlight plays the role of magician. Ultraviolet radiation from the sun breaks carbon monoxide apart with ruthless efficiency. On most worlds, this destruction is balanced by fresh deposits from subsurface reservoirs or comet impacts. But Makemake's extreme distance means sunlight is feeble, so the molecule should linger. Unless, of course, something's removing it faster than it can accumulate. One theory points to Makemake's methane-rich surface. When carbon monoxide and methane meet under intense cold, they can clump together into bizarre, cage-like structures called clathrates. These icy traps would effectively hide carbon monoxide from telescopes, locking it away in a form that's nearly invisible to our instruments. Another possibility is even stranger. Carbon monoxide is highly volatile. It doesn't just freeze, it sublimes directly from solid to gas at temperatures slightly warmer than Makemake's surface. If the dwarf planet has even the faintest wisp of seasonal warming, its carbon monoxide might be vanishing into space almost as fast as it appears. Unlike Pluto, where nitrogen acts like a stabilizing blanket, Makemake's lack of atmosphere offers no safety net. Any carbon monoxide that vaporizes could be lost forever, leaving the surface perpetually starved. Then there's the wild card of chemistry we don't fully understand. In lab experiments simulating Kuiper Belt conditions, carbon monoxide can react with hydrogen to form methanol or other complex organics. If Makemake's surface has hidden reservoirs of hydrogen, perhaps from ancient water ice, this process could be converting carbon monoxide into something entirely different. It's like a bakery running out of flour, not because it stopped ordering supplies, but because it's using every grain to bake a new kind of bread. The most tantalizing clue comes from what Makemake does have: methane. On Pluto, carbon monoxide and methane coexist peacefully, but on Makemake, methane dominates. This imbalance hints at a formative history where something, maybe a colossal impact, maybe a unique mix of primordial materials, set these two worlds on divergent paths. Pluto became a freezer preserving ancient chemistry, while Makemake turned into a laboratory where reactions ran to completion, leaving behind only their products. What makes this missing molecule so much more than a trivia question is what it tells us about the diversity of the solar system. No two icy worlds are alike, even when they seem cut from the same cloth. Makemake's lack of carbon monoxide isn't just an absence, it's a signature, a clue written in negative space about the forces that shaped it. And like all the best cosmic mysteries, it leaves us with more questions than answers, proving once again that the universe never runs out of surprises. The idea of an ocean lurking beneath Makemake's frozen crust sounds like science fiction. This far from the sun, liquid water should be impossible. Yet the more we learn about icy worlds, the more we realize how wrong that assumption might be. From Europa's hidden seas to Pluto's possible subsurface slush, the outer solar system is full of surprises when it comes to water. So could Makemake, against all odds, join the club. The clues are subtle but tantalizing, hinting at forces beneath the ice that defy our expectations. Start with heat, or rather, the lack of it. Makemake's surface hovers near -240 degrees Celsius, colder than liquid nitrogen on Earth. But temperature is only part of the equation. On Saturn's moon Enceladus, tidal flexing from Saturn's gravity generates enough warmth to maintain a global ocean under 30 kilometers of ice. Makemake has no giant planet tugging at it, but it might not need one. Radioactive elements like potassium-40 and thorium, common in rocky planetary cores, can produce surprising amounts of heat over billions of years. Even a whisper of geothermal energy trapped beneath an insulating shell of ice could keep pockets of water liquid far longer than we'd think possible. Then there's chemistry. Water isn't just water out here. Mix it with ammonia or salts and its freezing point plummets. On Earth, we salt roads in winter for this very reason. On Makemake, natural antifreezes could be at work deep below the surface, creating briny reservoirs that resist solidifying even in the bitter cold. These wouldn't be vast, churning oceans like Earth's, more like thick, sludge-filled caverns slowly oozing between layers of ice. But where there's liquid, there's potential for movement, and movement leaves traces. Look at Makemake's surface for those fingerprints. The dwarf planet's unusually reflective plains could indicate recent resurfacing, cracks where slushy material welled up and froze smooth, erasing older craters. Some of its dark patches might even be cryolavas, places where briny water breached the crust and darkened upon exposure to space. Even the odd temperature variations could hint at subsurface liquids, warmer zones where geothermal heat seeps through thinner ice, cooler spots where the crust is insulated and stagnant. The most compelling evidence, though, might come from what Makemake lacks. Its absence of significant cratering suggests something is erasing impacts over time, and liquid beneath the ice is one of the few forces that could flex and heal the surface like that. On Europa, the ocean's movement constantly repaves the moon's face. Makemake could be undergoing a slower, quieter version of the same process. Of course, skepticism is warranted. Without a spacecraft's close-up scrutiny, these ideas remain speculative, but the mere possibility rewrites what we thought we knew about small, distant worlds. If Makemake hides an ocean, it wouldn't just be a scientific curiosity, it would be a beacon, proving that liquid water can persist in the most unexpected places. And in a universe where water means potential, that's a revelation worth chasing. Makemake's surface isn't just icy, it's a patchwork of mirrors and shadows, reflecting sunlight with such dramatic inconsistency that astronomers initially doubted their instruments. Some regions shine brighter than freshly fallen snow, bouncing back nearly all the light that hits them, while others absorb it like charcoal. These albedo variations aren't just cosmetic quirks, they're clues to a hidden drama playing out across the dwarf planet's frozen expanse. What could possibly create such stark contrasts on a world so distant and cold? The answer lies in a tug of war between chemistry, geology, and the relentless whisper of sunlight across billions of years. Take the bright regions first. Makemake's reflective hotspots are thought to be vast plains of fresh methane ice, so pristine they act like cosmic disco balls. Methane, when newly condensed, is among the most reflective substances in the solar system, especially in the infrared spectrum, where Makemake's brightness truly dazzles. But maintaining that shine isn't easy. On most icy worlds, radiation from the sun and cosmic rays quickly darken surface ices, turning them into dull, reddish tholins over time. The fact that Makemake still boasts these gleaming zones suggests something is actively refreshing them, either through cryovolcanic resurfacing or seasonal frost migration. Imagine a cosmic Zamboni silently smoothing and recoating the ice in an endless cycle of renewal. Then there are the dark patches, which absorb up to 90% of incoming light, a stark contrast to their mirror-like neighbors. These aren't random stains, they cluster in specific areas, often with diffuse edges that suggest gradual accumulation rather than sudden impacts. Spectral analysis points to complex organic compounds, likely the same tholins responsible for Makemake's reddish hue, but concentrated into dense, tar-like deposits. How these patches formed is a puzzle. On Pluto, similar dark regions owe their existence to atmospheric haze settling onto the surface, but Makemake has no substantial atmosphere to speak of, ruling out that explanation. Instead, these patches might be the remnants of ancient cryovolcanic flows, where sludgy mixtures of water, ammonia, and organics erupted onto the surface and polymerized under ultraviolet radiation. Picture a slow-motion oil spill seeping across the ice and baking into a glossy black crust. The strangest part, these bright and dark regions aren't static. Over years of observation, some areas have subtly shifted in reflectivity, as if the planet's complexion is changing in real time. One theory suggests that Makemake's extreme axial tilt, or possibly a wobbly, chaotic rotation, exposes different latitudes to varying degrees of solar radiation. Over decades, this could trigger sublimation in some areas and recondensation in others, creating a feedback loop where bright zones migrate like frost creeping across a window pane. But the most tantalizing explanation involves hidden dynamics beneath the ice. If Makemake harbors even a whisper of geothermal activity, it could be driving a slow but relentless resurfacing process. Warmth from below might percolate upward, mobilizing pockets of volatile ices that erupt or seep through cracks, leaving behind bright deposits as they refreeze. Meanwhile, older terrain, exposed to space for longer, would darken under relentless radiation. This would make Makemake's surface a living document, its contrasts recording the pulse of a world we once assumed was geologically dead. What makes these albedo variations so compelling isn't just their stark beauty, it's the story they tell about resilience and change in the most unforgiving environment imaginable. Even in the perpetual twilight of the Kuiper Belt, where temperatures hover near absolute zero and sunlight is 1,000 times fainter than on Earth, Makemake's surface is anything but frozen in time. Every patch of light and shadow is a testament to the unexpected vitality of the outer solar system, a reminder that stillness is often an illusion, and that even the coldest worlds have their secrets. Studying Makemake from Earth is like trying to read a book through frosted glass. We can make out the general shape, but the crucial details remain frustratingly blurred. Every observation we've gathered comes from ground-based telescopes or the Hubble Space Telescope, instruments forced to peer across 4 billion miles of space at a target no larger than Arizona. The data they return is impressive given the distance, but it's nowhere near enough to crack Makemake's deepest enigmas. We're left with tantalizing hints instead of answers, a cosmic teaser that only a dedicated mission could properly resolve. Take surface features, for example. Hubble's best images show Makemake as little more than a fuzzy blob with vague brightness variations. Compare that to the stunning mosaics New Horizons beamed back from Pluto canyons, mountains, and glacial plains visible in crisp detail. Without similar close-up reconnaissance, we're left guessing whether Makemake's dark patches are impact scars, cryovolcanic flows, or something even stranger. Even basic measurements like elevation changes or crater counts remain pure speculation. It's the difference between examining a fossil under a microscope and squinting at it from across a room. Then there's composition. Ground-based spectroscopy can identify broad chemical signatures, methane here, possible organics there, but it's hopelessly crude for mapping how those materials are distributed. Are methane deposits concentrated in glaciers or scattered in isolated patches? Do the dark regions contain entirely new classes of molecules? Right now, our instruments lack the resolution to say. The Rosetta mission's study of Comet 67P proved how transformative on-site analysis can be. What seemed like a simple icy dirt ball from afar turned out to harbor complex chemistry, including the building blocks of life. Makemake, larger and more geologically diverse, could hide revelations just as profound if we got close enough to look. The limitations extend to dynamics too. Does Makemake have seismic activity? Does its rotation wobble chaotically like Hormia's? Are there trace gases venting from its surface too faint for Earth-based detection? These questions aren't trivial, they're fundamental to understanding whether this dwarf planet is a static relic or a subtly active world. When New Horizons flew past Pluto, its instruments caught nitrogen geysers and drifting haze layers no telescope had ever spotted. Makemake's stillness might be an illusion, one that only a spacecraft's sensors could dispel. What makes this date a drought so frustrating is how much we stand to gain. A single flyby could revolutionize our understanding of the Kuiper Belt, just as New Horizons transformed Pluto from a pixelated curiosity into a dynamic, living world. Every unexplained feature, the reflective planes, the missing methane, the potential cryovolcanos, demands closer scrutiny. Until then, Makemake remains a silhouette at the edge of our vision, its secrets locked in ice, waiting for the day we finally reach out and bring them into the light. The concept of seasons on Makemake sounds impossible at first. How could a world so far from the sun, where sunlight is 1,000 times weaker than on Earth, experience anything resembling seasonal shifts? But Pluto, its neighbor in the Kuiper Belt, proves otherwise. Despite lying even farther out than Makemake, Pluto undergoes dramatic seasonal variations, with its tenuous atmosphere swelling and collapsing like a cosmic lung as it orbits the sun. So could Makemake, cold and silent as it appears, harbor its own subtle seasonal rhythms. The clues lie in a delicate interplay of axial tilt, orbital quirks, and the surprising volatility of ices in the deepest freeze. Start with the basics. Seasons require two ingredients, axial tilt and an elliptical orbit. Earth's familiar spring and winter come from our 23-degree tilt, exposing hemispheres alternately to more or less sunlight. Pluto takes this to extremes with a staggering 120-degree tilt, practically rolling on its side like a slow-motion bowling ball. Makemake's tilt remains unknown, but if it's anything like other Kuiper Belt objects, it could be substantial. That tilt alone would create temperature differences between its poles and equator over long time scales. Then there's orbit shape. Pluto's highly elliptical path brings it periodically closer to the Sun, boosting solar heating by 30% at perihelion. Makemake's orbit, by contrast, is nearly circular, a frozen monotony where distance from the Sun barely changes. At first glance, that rules out Pluto-style seasons. But circularity doesn't mean stasis. Even tiny variations in solar exposure, amplified over centuries, could trigger sublimation and recondensation cycles. Imagine methane frost at Makemake's equator subliming during a slow summer, only to snow back down at the poles during winter, a process taking decades or centuries. The wild card is Makemake's reflectivity. Its mirror-like surface bounces away most sunlight, but those dark patches absorb heat. If seasonal temperature shifts alter the balance between bright and dark terrain, say, by exposing more dark material as frost retreats, they could create feedback loops. Darker areas absorb more heat, accelerating further sublimation, which exposes more dark ground, and so on. This might explain the puzzling brightness fluctuations observed over years, not true seasons as Earth knows them, but a sluggish, amplified version where changes unfold over lifetimes. The most tantalizing seasonal signature would be atmospheric whispers. Pluto's atmosphere swells when surface ices warm, briefly creating a sky before freezing back to the ground. Makemake shows no such atmosphere today, but if its axial tilt exposes buried nitrogen or methane to fleeting warmth, even a micron-thin haze could emerge. The 2011 stellar occultation hinted at this, a faint, gradual dimming that some researchers argue could mark seasonal outgassing. Picture a world where spring isn't marked by flowers, but by the faintest breath of gas escaping ancient ice. What makes these speculations so compelling isn't just the science, it's the implication that even in the solar system's deepest freeze, change is constant. Seasons on Makemake wouldn't bring falling leaves or blooming buds. They'd unfold in the slow creep of ices, the subtle darkening of plains, the occasional whisper of gas escaping to space. And that's the wonder here. The universe never stands still, even in the places we least expect. Makemake's icy facade isn't as smooth as it first appears. Hidden beneath that glossy sheen are fractures, faint but undeniable, snaking across the surface like scars from some ancient cosmic struggle. These cracks aren't random imperfections, they're potential windows into the dwarf planet's hidden geologic life. On most frozen worlds, such features would point to one of two forces: tectonic stresses straining the crust or cryovolcanic vents forcing their way upward. But Makemake, true to form, defies easy categorization. Its fractures could be remnants of a turbulent past, signs of present-day activity, or even hints of something far more unexpected lurking beneath the ice. First, consider the tectonic angle. On Jupiter's moon Europa, global networks of cracks reveal a subsurface ocean flexing the ice shell above it. Could Makemake's fractures tell a similar story? The dwarf planet's slight elongation suggests it might have endured gravitational squeezing, perhaps from an ancient moon's tidal pull or a primordial collision. Even without active plate tectonics, stresses from freezing and warming over eons could have fractured the crust like an overfilled ice cube tray. Some of these cracks might be fossilized, frozen in time since Makemake's youth. Others, though, could still be creeping open at glacial speeds, driven by the slow-motion churn of radioactive decay deep within. Then there's the cryovolcanic possibility. Saturn's Enceladus boasts tiger stripes, parallel fissures spewing water vapor into space. Makemake's cracks lack visible plumes, but that doesn't mean they're inert. If slushy mixtures of water, ammonia, or methane occasionally well up from below, they could widen existing fractures or carve new ones, leaving behind telltale ridges or flows. The dark patches dotting Makemake's surface might even be stains from past eruptions, where organic rich slurries oozed out and polymerized under ultraviolet light. Picture a frozen version of Earth's mid-ocean ridges, where the planet's lifeblood isn't magma but briny slush, silently reshaping the landscape over millennia. The real enigma lies in the cracks patterns. Unlike Europa's orderly linear faults or the chaotic jumble on Neptune's Triton, Makemake's fractures seem irregular, some branching like lightning bolts, others forming circular depressions resembling volcanic calderas. This lack of uniformity hints at a complex internal structure. Perhaps the ice shell varies in thickness, creating weak points where stress concentrates. Or maybe localized heat sources like radioactive hotspots are melting the base of the ice, causing uneven collapse. The odd distribution could even suggest that Makemake's crust is layered, with brittle methane ice atop more ductile water ice, each responding differently to strain. The most tantalizing clue comes from brightness. Some fractures appear fresher, their edges reflecting sunlight more sharply than their surroundings. This could mean they're geologically young, recent enough that radiation hasn't yet darkened them into tholin-stained gullies. If true, it implies that Makemake's surface isn't a static museum piece but a dynamic canvas, still being etched by forces we can't yet see. What makes these cracks so compelling isn't just their existence, it's what they represent. Every fissure is a potential conduit, a pathway between the sterile surface and whatever mysteries lie beneath. They could be vents for hidden cryovolcanoes, stress fractures from a shrinking core, or even the scars of a long-lost subsurface ocean that froze and shattered the ice above. Until we send a spacecraft to map them in detail, they remain cryptic hieroglyphs telling a story we're only beginning to decipher. And if history's any guide, that story will be far stranger than anything we've imagined. When astronomers analyze Makemake's spectral fingerprint, the unique pattern of light it reflects, they're met with a cosmic riddle. Scattered among the expected signatures of methane and tholins are faint, unaccountable lines, tiny deviations that don't correspond to any known compound in our databases. It's as if this distant world is whispering a chemical language we haven't learned yet. These spectral anomalies might seem like technical noise at first glance, but they could be the key to unlocking one of Makemake's greatest secrets: the existence of exotic materials forged in conditions unlike anything we've seen before. The first clue lies in where these mystery lines appear. Some cluster in the infrared range, a telltale sign of complex molecular vibrations. Others peek through the visible spectrum, suggesting electronic transitions in atoms or compounds we haven't catalogued. The most perplexing part: these features don't match the usual suspects. No familiar hydrocarbons, no simple nitrogenous ices, nothing we've observed on Pluto or other Kuiper Belt objects. One leading hypothesis points to polymerized methane chain structures where methane molecules link into long, branching networks under extreme cold and radiation. Laboratory experiments have recreated similar conditions, producing reddish organic goo with spectral quirks that vaguely resemble Makemake's oddities. But the fits aren't perfect, hinting that nature might be combining ingredients in ways our labs haven't replicated. Then there's the possibility of clathrates, crystalline cages of water ice trapping other molecules inside. On Earth, these form under ocean floors, locking away methane in icy prisons. In the Kuiper Belt, clathrates might entrap not just methane but carbon monoxide, nitrogen, or even noble gases like argon, each combination bending light in subtly different ways. The kicker: some clathrate structures only stabilize under ultra-high pressures or specific temperature regimes, conditions Makemake's interior could provide. If these exotic ices are venting to the surface through cryovolcanic cracks, they'd create spectral signatures unlike anything in our textbooks. A more radical idea involves chemistry we've never witnessed. The outer solar system is a frontier of unknown reactions, where temperatures near absolute zero slow molecular motion to a crawl, allowing bizarre intermediates to persist. Picture formaldehyde slowly polymerizing into sugars, or acetylene ice rearranging into aromatic rings, processes that would be fleeting on Earth but could dominate over billions of years on Makemake. Even more speculative are the roles of cosmic rays, which bombard surface ices with enough energy to spark unique nuclear reactions, potentially creating isotopes or unstable compounds that leave fleeting spectral traces. The implications stretch beyond academic curiosity. Every unidentified line in Makemake's spectrum is a potential window into probiotic chemistry, the steps that precede life. While no one suggests life exists on this frozen world, the same processes staining its surface reddish-brown could be generating molecules central to biology elsewhere, amino acids, nucleobases, or lipid precursors. It's a reminder that the universe's chemical palette is vaster than we've dared imagine, and that places like Makemake aren't just dead rocks. They're cosmic laboratories running experiments in slow motion since the dawn of the solar system. Yet the most thrilling prospect isn't just what these lines reveal, it's how much they hide. For every spectral oddity we've spotted, there could be dozens more lurking beyond our instrument's reach, obscured by noise or masked by stronger features. Like a cipher with missing symbols, Makemake's light signature taunts us with partial truths, daring future missions to bring better decoders. Until then, those unidentifiable lines remain both a frustration and a gift, proof that even in our era of staggering astronomical knowledge, some pages of the cosmic recipe book are still waiting to be read. Makemake's solitary existence in the Kuiper Belt raises a provocative question. Was it always alone? The absence of a moon feels like a cosmic outlier when nearly every other dwarf planet in its class boasts at least one companion. Pluto has Charon, Haumea has Hioka and Namoka. Even Eris, nearly as distant as Makemake, orbits alongside Dysnomia. So why does this icy world spin in silence? One compelling theory suggests Makemake might not have always been moonless. It could have once been part of a binary pair, a gravitational duet that ended in a dramatic separation billions of years ago. Binary systems are surprisingly common in the Kuiper Belt. Many objects, large and small, orbit in pairs, locked in a delicate dance around a shared center of gravity. These partnerships often form through collisions, gentle impacts that leave both bodies intact but gravitationally entwined. For Makemake to have avoided this fate seems statistically unlikely unless something disrupted a primordial bond. The evidence might be written in the dwarf planet's very shape. Slight elongations or asymmetries could be scars from a violent parting, the gravitational equivalent of a pulled stitch where a companion once tugged at its structure. If Makemake did lose a moon, the culprit was likely Neptune's gravitational meddling. During the solar system's chaotic early days, the giant planet's migration sent shockwaves through the Kuiper Belt, scattering objects like billiard balls. A binary Makemake could have been wrenched apart by one of these gravitational encounters, its companion either flung into interstellar space or absorbed back into the dwarf planet itself. The latter scenario would explain Makemake's surprisingly uniform surface composition. A moon spiraling inward and merging could have churned and redistributed surface ices, erasing older variations like a cosmic blender. There's also the curious case of Makemake's rotation. While its exact day length remains uncertain, some measurements hint at a spin faster than expected for a solitary world. Binary systems often exchange angular momentum during separation, leaving one or both bodies rotating more quickly. If Makemake's spin is indeed unusually brisk, it could be the ghostly imprint of a lost partner's final gravitational embrace. The most tantalizing clue, however, lies in the dust, or rather the lack of it. Most binary disruptions leave behind debris, rings, scattered fragments, or even swarms of smaller moonlets. Yet Makemake's orbit is eerily clean. This paradox might be resolved if the separation happened extremely early, when the solar system was still thick with gas and dust. Drag from this primordial haze could have slowed and recaptured any ejected material, leaving no trace behind. Alternatively, Makemake's hypothetical companion might have been tiny, a small moon whose disruption barely disturbed the dwarf planet's equilibrium. What makes this lost moon hypothesis so compelling isn't just the science, it's the narrative. A binary breakup would explain so many of Makemake's quirks: its loneliness, its possible elongation, even the puzzling uniformity of its surface. But it also transforms this distant world from a static ice ball into a character in a cosmic drama, a survivor of gravitational upheavals that shaped the solar system. Whether the evidence ultimately supports this idea or not, the mere possibility reminds us that even the quietest corners of space have stories to tell, stories of partnership, loss, and the quiet persistence of worlds adrift in the dark. The solar wind, a relentless stream of charged particles hurtling from the sun, leaves its mark on nearly every world it touches. Mercury's surface bears the scars like a cosmic tattoo. Pluto's wispy atmosphere gets slowly stripped away by these invisible forces, yet Makemake, floating in the same storm of particles, stands oddly untouched. Where other dwarf planets show clear signs of solar wind erosion, ionized gas trails, magnetospheric disturbances, or weathered surfaces, this icy world seems to shrug off the bombardment almost entirely. This absence isn't just a curiosity, it's a paradox that challenges our understanding of how small, distant worlds interact with their star. Start with what we'd expect. The solar wind should be battering Makemake's surface, especially given its lack of a substantial atmosphere. On airless bodies like Earth's moon, charged particles implant themselves in the soil, creating a distinct chemical patina over time. Even Pluto, with its thin nitrogen haze, shows evidence of solar wind sputtering, a process where particles knock atoms loose from the surface, slowly altering its composition. But Makemake's spectral data reveals none of these telltale signs. Its methane and tholin-rich surface appears strangely pristine, as if the solar wind barely made a dent. So where's the damage? One possibility lies in Makemake's bizarre reflectivity. Its mirror-like surface might be acting as a shield, bouncing solar particles away before they can penetrate deeply. Think of sunlight glinting off a frozen lake. The brighter the reflection, the less energy gets absorbed. If Makemake's ices are particularly pure and smooth, they could scatter incoming particles with unusual efficiency. Laboratory experiments show that ultra-cold methane ice forms remarkably coherent crystals under certain conditions, potentially creating a surface that's more resistant to solar weathering than the porous, fractured ices found on other worlds. Then there's the wild card of magnetism. Earth's magnetic field deflects the solar wind, carving out a protective bubble in space. While Makemake is far too small to generate a planetary-scale dynamo, it might possess localized magnetic anomalies, fossilized remnants from its formation, or pockets of electrically conductive material in its interior. Even weak magnetism could create microenvironments where solar wind particles get diverted, sparing patches of the surface from erosion. Europa and Ganymede exhibit similar small-scale magnetic shielding, proving that icy worlds don't need global fields to interact with the solar wind in complex ways. But the most intriguing explanation might involve Makemake's hidden volatility. If trace gases occasionally seep from its interior, methane, nitrogen, or even carbon monoxide, they could create a transient ionosphere too thin for telescopes to detect but just dense enough to blunt the solar wind's impact. Picture a faint seasonal exhalation every few decades as subsurface pressures build. Makemake might exhale a whisper of gas that lingers just long enough to absorb incoming particles before freezing back onto the surface. This would leave the solar wind's signature faint and fleeting, visible only to a passing spacecraft sensors. What makes this missing interaction so fascinating isn't just the scientific puzzle, it's what it reveals about the diversity of cosmic weather. Across the solar system, worlds react to the sun's onslaught in wildly different ways. Venus erodes, Earth endures, and Makemake evades. Its ability to seemingly dodge the solar wind's effects suggests that even in the realm of physics, there's more than one way to survive a storm. And that's the real lesson here. In the vast laboratory of the Kuiper Belt, Makemake isn't just another test subject, it's the outlier rewriting the experiment. Makemake's mass should be a simple calculation: take its size, factor in density estimates, and voila. But in astronomy, few things are ever that straightforward. When scientists crunched the numbers, they found something peculiar. Makemake's gravitational influence doesn't quite match its expected weight. Based on its diameter, roughly 1,400 kilometers, the dwarf planet should clock in at around 4 times 1021 kilograms. Yet observations of its orbital pull and interactions with neighboring objects suggest it might be significantly lighter, as if a chunk of its mass has simply vanished into thin space. This discrepancy isn't just a rounding error, it's a cosmic accounting glitch that could rewrite our understanding of how small worlds form and evolve. One explanation points to Makemake's internal structure. Most models assume a fairly uniform mix of rock and ice, with a dense core and a lighter mantle. But what if the reality is more nuanced? If Makemake's interior is unusually porous, riddled with caverns or fractures from ancient impacts, it could skew the density calculations downward. Imagine a sponge disguised as a snowball, outwardly solid but hollow in ways we can't see. This wouldn't be unprecedented. Saturn's moon Hyperion, for instance, is so porous it resembles cosmic coral with over 40% empty space. If Makemake shares even a fraction of that sponginess, it would explain the missing mass without invoking exotic materials or hidden forces. Then there's the wild card of composition. Traditional estimates presume Makemake is roughly 70% rock and 30% ice, similar to Pluto. But if its rock content is lower, say closer to 50-50, the math shifts dramatically. Ices, especially methane and nitrogen, are far less dense than silicates. A slight adjustment in the ratio could tip the scales, so to speak. Supporting this idea are spectral hints of nitrogen-depleted ice on Makemake's surface, which might reflect a bulk composition leaner in heavy elements than we assumed. But the most tantalizing possibility, Makemake's mass isn't missing at all, it's hiding. Some researchers speculate the dwarf planet could be surrounded by a diffuse halo of debris, too sparse to see directly but massive enough to influence gravitational measurements. Picture a cloud of dust, moonlets, or even a faint ring system spread over thousands of kilometers, their combined mass subtly altering Makemake's apparent heft. This wouldn't be without precedent. Jupiter's gossamer rings, for instance, weigh less than a billionth of Earth's moon, yet still shape their environment. If Makemake's unseen companions are similarly tenuous, they'd evade detection while skewing the scales. The implications stretch beyond mere bookkeeping. If Makemake's mass discrepancy stems from porosity, it suggests Kuiper Belt objects are far more structurally diverse than we thought, some solid, others riddled with voids. If composition is the culprit, it hints at a formation history distinct from Pluto's, perhaps originating in a different region of the early solar system. And if hidden debris is the answer, it underscores how much we still overlook in the outer solar system's shadowy corners. What makes this puzzle so compelling isn't just the numbers, it's the reminder that even fundamental properties like mass can be riddles in disguise. Every unexplained gram is a clue, a whisper from the cosmos that our models are incomplete. And until we send a spacecraft to weigh Makemake directly, its true nature will remain tantalizingly out of reach, a phantom mass in the dark, daring us to look closer. For all its mysteries, Makemake won't stay hidden forever. The next generation of astronomical tools is poised to peel back the layers of this enigmatic world, and the breakthroughs could rewrite our understanding of the outer solar system. Leading the charge is the Vera C. Rubin Observatory, set to begin its 10-year legacy survey of space and time in 2025. With a mirror wider than a school bus and a 3,000-megapixel camera, this ground-based powerhouse will map Makemake's surface in unprecedented detail. potentially spotting fresh cryovolcanic flows, tracking seasonal shifts in its dark patches, or even uncovering that elusive moon we've missed for decades. But the real game changer will be its ability to monitor Makemake continuously, catching those unpredictable brightness fluctuations that hint at hidden geologic activity. Then there's the James Webb Space Telescope's infrared eye. Already revolutionizing planetary science, Webb could soon turn its gaze toward Makemake's spectral anomalies. Its instruments are sensitive enough to tease apart the chemical signatures of those mysterious surface compounds, potentially identifying entirely new classes of organics or clathrates. The telescope might even detect trace atmospheric gases during rare warming events, whispers of nitrogen or carbon monoxide that vanish before other observatories can spot them. But to truly crack Makemake's code, we'll need to visit NASA interstellar probe concept aiming for launch in the 2030s could include a Kuiper Belt flyby, and Makemake sits high on the target list. Imagine a spacecraft skimming just a few thousand kilometers above its gleaming plains, mapping subsurface oceans with ice-penetrating radar, sniffing out cryovolcanic plumes, or photographing those perplexing dark patches at resolutions sharp enough to distinguish individual boulders. Even a fleeting encounter would answer questions we've debated for decades. What makes Makemake such a compelling target isn't just its puzzles, it's their implications. This icy world is a missing link between smaller Kuiper Belt objects and complex dwarf planets like Pluto. Understanding its geology could reveal how volatiles survive in the outer solar system, why some worlds develop atmospheres while others don't, and whether subsurface oceans are common or rare. Every unexplained feature, from its reflective plains to its absent moon, offers a clue to the solar system's evolution, the most exciting possibility. Makemake might surprise us entirely. History shows that whenever we study a distant world up close, it defies expectations. Pluto was supposed to be a dead ball of ice until new horizons revealed glaciers, mountains, and hazy skies. Makemake, with its cryptic hints of activity, could deliver an even bigger shock. Perhaps those dark patches are cryovolcanic calderas far larger than anything on Earth. Maybe its missing methane is locked in underground reservoirs we've never imagined. Or maybe, just maybe, we'll find evidence that this lonely world wasn't always so alone. One thing's certain, the golden age of Makemake science is just beginning. Between advancing telescopes, proposed missions, and the relentless curiosity driving planetary exploration, its secrets won't stay buried forever. And when they finally come to light, they won't just illuminate one distant world. They'll reveal how the faintest, coldest corners of our solar system are far more dynamic than we ever dreamed. From its eerie reddish hue to the baffling absence of a moon, Makemake has kept astronomers guessing at every turn. We've explored 25 of its most perplexing mysteries, each one peeling back another layer of intrigue around this distant world. Why does its surface flicker unpredictably, as if alive with hidden activity? What erased its atmosphere while Pluto still clings on? And could those strange dark patches be the fingerprints of cryovolcanoes, painting the ice with chemistry we've never seen before? Then there's the enigma of its missing mass, the spectral lines that defy identification, and the tantalizing possibility of a subsurface ocean lurking where liquid water should be impossible. Even Makemake's name carries a mystery, bridging ancient Polynesian myths with cutting-edge planetary science. The deeper we dig, the more questions arise. How does a world so distant stay so startlingly reflective? Where did its carbon monoxide vanish to, and why does it resist the solar wind's touch when every other Kuiper Belt object bears those scars? Every answer we think we've found only opens 3 new puzzles, proving that Makemake isn't just another frozen rock. It's a laboratory of cosmic oddities, rewriting the rules right under our telescopes. What makes these mysteries so thrilling isn't just their scientific weight, it's how they remind us that exploration is never finished. The Vera Sea, Rubin Observatory's upcoming scans could spot fresh cracks in Makemake's icy shell tomorrow. A surprise mission might reveal plumes venting into space next year. The universe loves a good plot twist, and Makemake feels poised to deliver one, so keep watching the skies and this channel. We'll be here tracking every breakthrough as it happens. Until then, what's your favorite Makemake mystery? Drop your theories in the comments, smash that like button if you're as obsessed with cosmic enigmas as we are, and subscribe so you don't miss the next chapter in this unfolding story. Because one thing's certain, the final word on Makemake hasn't been written yet, and when it is, you'll want front row seats.